We have now reached the point in the course where we're going to be learning about the motion of objects moving in circles and the motion of rotating objects. However, before we can start to understand those motions, first we have to be able to describe them. So in this video, I'm going to begin introducing you to rotational kinematics. Rotational kinematics is the subject where we learn to describe the motion of objects which are rotating and which are moving in circles. Once we can describe rotational motion and circular motion, then we can begin to understand why rotating objects and objects moving in circles move as they do. But first, we need to be able to simply describe that motion. Over here, I've begun drawing a figure to introduce us to our first concept in rotational kinematics. We're going to say that we have a mouse here, and that mouse is going to run around this circle here. Anytime we wish to describe the motion of an object moving in a circle, we start by drawing a reference line. The reference line starts at the center of the circle and then generally goes out towards the right. Once we have drawn the reference line, we can locate an object at any other point on the circle by drawing a radius out to that object and then giving the angle between the reference line and the radius out to our object. For example, here I've drawn the mouse sitting at this particular point on the circle. So I have a radius that goes out to the mouse, and then a 30-degree angle between our reference line and the radius which goes out to the mouse. That 30-degree angle locates the mouse on our circle. Now let's describe a motion where the mouse starts at the reference line and moves round and round the circle. We're going to say that at time equals 0, the mouse is located at the reference line. At time equals 1 second, the mouse is located at 30 degrees. At time equals 2 seconds, the mouse is located at 60 degrees. And at time equals 3 seconds, the mouse is located at 90 degrees. Here's what I'd like you to try to do. Look at what the mouse is doing, and then pause the video and see if you can write down an English sentence which describes what is going on with the mouse. Here's how I would describe the motion of the mouse. I would say that the angular position of the mouse changes by 30 degrees in every 1 second interval. Or in other words, we can say every second, the angular position of the mouse changes by 30 degrees. Equivalently, we could say that the angular position of the mouse changes at a rate of 30 degrees per second. I've given you a couple of new ideas here. First, an object moving in a circle can be located by its angular position, and that angular position can change at a particular rate. Let's call the rate at which the angular position changes the angular velocity. So the angular velocity is the rate at which the angular position changes. Notice that I have introduced here a symbol for the angular velocity. This is the Greek letter omega. For reasons I don't quite understand, my students will often refer to omega as if it were a letter of the Latin alphabet. So there's some letter at the end of the Latin alphabet, it's X or V or one of those, that somehow my students get omega mixed up with that one. But we're not going to do that. We're going to remember that this is a Greek letter omega, not a letter of the Latin alphabet. Now I'd like to develop the idea of angular velocity a bit more formally. You can see that I have drawn a circle again with a reference line. I have also drawn this arrow hooking counterclockwise with a little plus sign. This notation means that we are taking counterclockwise to be our positive direction for rotation. One thing that tells us is that as an object moves around the circle counterclockwise, its angular position increases. And when an object moves around the circle in a clockwise fashion, the angular position decreases. In some instances, we could decide to take clockwise to be our positive direction for rotation, but most often we take counterclockwise as the positive direction. So anyway, I have an object moving on a circle indicated by this blue-green dot. At time t0, the dot is at angular position theta 0. At time t1, the dot is at angular position theta 1. So let's say that we're talking about a time interval that goes from time 0 to time 1. We would then have delta t equals t1 minus t0. The change in angular position during that time would then be delta theta equals theta 1 minus theta 0. Getting now to the angular velocity. We can always say that the average angular velocity is equal to a change in angular position divided by the time interval during which that change in angular position occurred. So this formula for the average angular velocity is always true. Now, is it ever true that the actual angular velocity is given by the same formula, delta theta over delta t? That question brings us to the idea of constant angular velocity. We say that the angular velocity of an object is constant when the angular position changes by equal amounts in equal time intervals. So what would be an example of motion with constant angular velocity? Well, our mouse from earlier was moving with a constant angular velocity. For every 1 second time interval, the mouse went through the same change in angular position, namely 30 degrees. So this mouse here was moving with a constant angular velocity equal to 30 degrees per second. So coming back to my earlier question, when can we say that the angular velocity itself is actually equal to delta theta over delta t? We can say that the angular velocity itself is equal to this expression when the angular velocity is constant. Okay? So if the angular velocity is a constant, then we can say that the angular velocity is equal to the change in angle during some time interval divided by the time interval. So now we've had a bit of an introduction to rotational kinematics. I have introduced you to our first rotational kinematic quantity, namely the angular velocity. In the next video, we're going to do a sample calculation of angular velocity. And in the videos after that, I will be introducing you to additional rotational kinematic quantities and also to more formalism so that we can start doing actual problems with this stuff.